continuity, and differentiability. Introduction. In this chapter, we introduce the very important concepts of continuity, differentiability, and relations between them. We also learn differentiation of inverse trigonometric functions. Further, we introduce a new class of functions called exponential and logarithmic functions. These functions lead to powerful techniques of differentiation. We illustrate certain geometrically obvious conditions through differential calculus. Continuity. We start this section with two informal examples to get a feel of continuity. Consider the function f of x is equal to 1 if x is lesser than or equal to 0, and 2 if x is greater than 0. This function is of course defined at every point of the real line. Graph of this function is given in the figure. One can deduce from the graph that the value of the function at nearby points on x-axis remain close to each other except at x is equal to 0. At the points near and to the left of 0, that is, at points like minus 0.1, minus 0.01, minus 0.001, the value of the function is 1. At the points near and to the right of 0, that is, at points like 0.1, 0.01, 0.001, the value of the function is 2. Using the language of left and right-hand limits, we may say that the left, respectively right-hand limit of f at 0 is 1, respectively 2. In particular, the left and right-hand limits do not coincide. We also observe that the value of the function at x is equal to 0 coincides with the left-hand limit.
Note that when we try to draw the graph, we cannot draw it one stroke, that is, without lifting pen from the plane of the paper. We cannot draw the graph of this function. In fact, we need to lift the pen when we come to 0 from left. This is one instance of function being not continuous at x equal to 0. Now, consider the function defined as f of x equal to 1 if x not equal to 0, 2 if x equal to 0. This function is also defined at every point. Left and the right hand limits at x equal to 0 are both equal to 1, but the value of the function at x equal to 0 equals 2, which does not coincide with the common value of the left and right hand limits. Again, we note that we cannot draw the graph of the function without lifting the pen. This is yet another instance of a function being not continuous at x equal to 0. We may say that a function is continuous at a fixed point if we can draw the graph of the function around that point without lifting the pen from the plane of the paper. Mathematically, it may be phrased precisely as follows.
Definition. Suppose f is a real function on a subset of the real numbers and let C be a point in the domain of f. Then f is continuous at C if limit x extends to C, f of x is equal to f of C. More elaborately, if the left-hand limit, right-hand limit, and the value of the function at x is equal to C exist and equal to each other, then f is said to be continuous at x is equal to C. Recall that if the right-hand and left-hand limits a, x is equal to C, coincide, then we say that the common value is the limit of the function at x is equal to C. Hence, we may also rephrase the definition of continuity as follows. A function is continuous at x is equal to C if the function is defined at x is equal to C and if the value of the function at x is equal to C equals the limit of the function at x is equal to C. If f is not continuous at C, we say f is discontinuous at C and C is called a point of discontinuity of f.
Examine whether the function f given by f of x is equal to x square is continuous at x is equal to 0. Solution. First note that the function is defined at the given point x is equal to 0 and its value is 0. Then find the limit of the function at x is equal to 0. Clearly, limit x to 0 f of x is equal to limit x to 0 x square is equal to 0 square, which is equal to 0. Thus, limit x to 0 f of x is equal to 0 is equal to f of 0. Hence, f is continuous at x is equal to 0.
Example, discuss the continuity of the function f given by f of x equal to determinant x at x equal to 0. Solution, by definition, f of x equal to minus x if x lesser than 0, x if x greater than or equal to 0. Clearly, the function is defined at 0 and f of 0 equal to 0. Left hand limit of the f at 0 is limit x tends to 0 f of x equal to limit x tends to 0 minus x equal to 0. Similarly, the right hand limit of f at 0 is limit x tends to 0 f of x equal to limit x tends to 0 x equal to 0. Thus, the left hand limit, right hand limit and the value of the function coincide at x equal to 0. Hence, f is continuous at x equal to 0. Example, check the points where the constant function f of x equal to k is continuous. Solution, the function is defined at all real numbers and by definition, its value at any real number equals k. Let c be any real number. Then, limit x tends to c f of x equal to limit x tends to c k equal to k. Since f of c equal to k equal to limit x tends to c f of x for any real number c. The function f is continuous at every real number. Example, prove that the identity function on real number given by f of x equal to x is continuous at every real number. Solution, the function is clearly defined at every point and f of c equal to c for every real number c. Also, limit x tends to c, f of x equal to limit x tends to c, x equal to c. Thus, limit x tends to c, f of x equal to c equal to f of c, and hence the function is continuous at every real number. Having defined continuity of a function at a given point, now we make a natural extensions of this definition to discuss continuity of a function. Definition.
A real function f is said to be continuous if it is continuous at every point in the domain of f. This definition requires a bit of elaboration. Suppose f is a function defined on a closed interval a, b, then for f to be continuous, it needs to be continuous at every point in a, b, including the endpoints a and b. Continuity of f at a and f at b is expressed as follows. Is the function defined by f of x is equal to modulus of x, a continuous function. Solution. We may write f as f of x is equal to minus x if x is lesser than 0, x if x is greater than or equal to 0. We know that f is continuous at x is equal to 0. Let c be a real number such that c is lesser than 0. Then f of c is equal to minus c. Also, limit x to c f of x is equal to limit x to c of minus x is equal to minus c. Since limit x to c f of x is equal to f of c, f is continuous at all negative real numbers. Now, let c be a real number such that c is greater than 0. Then, f of c is equal to c. Also, limit x to c f of x is equal to limit x to c x is equal to c. Since limit x to c f of x is equal to f of c, f is continuous at all positive real numbers. Hence, f is continuous at all points.
Example, Discuss the continuity of the function f given by f of x equal to x cube plus x square minus 1. Solution. Clearly, f is defined at every real number c and its value at c is c cube plus c square minus 1. We also know that limit x tends to c f of x equal to limit x tends to c x cube plus x square minus 1 equal to c cube plus c square minus 1. Thus, limit x tends to c f of x equal to f of c and hence f is continuous at every real number. This means f is continuous function. Example, discuss the continuity of the function f defined by f of x equal to 1 by x, x not equal to 0. Solution. Fix any non-zero real number c. We have limit x tends to c f of x equal to limit x tends to c 1 by x equal to 1 by c. Also, since for c not equal to 0, f of c equal to 1 by c, we have limit x tends to c equal to f of x equal to f of c and hence f is a continuous at every point in the domain of f. Thus, f is a continuous function. We take this opportunity to explain the concept of infinity. This we do by analyzing the function f of x equal to 1 by x near x equal to 0. To carry out this analysis, we follow the usual trick of finding the value of the function at real numbers close to 0. Essentially, we are trying to find the right-hand limit of f at 0. We tabulate this in the following table. We observe from the table that as x gets closer to the 0 from the right, the value of f of x shoots up higher. This may be rephrased as the value of f of x may be made larger than any given number by choosing a positive real number very close to 0. In symbols, we write the right-hand limit of f of x at 0 in plus infinity. We wish to emphasize that plus infinity is not a real number and hence the right-hand limit of f at 0 does not exist as a real number. Similarly, the left-hand limit of the f at 0 may be found. The following table is self-explanatory. From the table, we deduce that the value of f of x may be made smaller than any given number by choosing a negative real number very close to 0. In symbols, we write the left-hand limit of f of x at 0 is minus infinity. Again, we wish to emphasize that minus infinity is not a real number and hence the left-hand limit of f at 0 does not exist as a real number. The graph of the reciprocal function given in figure 5.3 is the geometric representation of the above mentioned facts. Example, discuss the continuity of the function f defined by f of x equal to x plus 2 if x lesser than or equal to 1, x minus 2 if x greater than 1. Solution. The function f is defined at all points of the real line. Case 1. If c lesser than 1, then f of c equal to c plus 2. Therefore, limit x tends to c f of x equal to limit x tends to c f of x plus 2 equal to c plus 2. Thus, f is continuous at all real numbers less than 1. Case 2. If c greater than 1, then f of c equal to c minus 2. Therefore, limit x tends to c f of x equal to limit x tends to c x minus 2 equal to c minus 2 equal to f of c. Thus, f is continuous at all points x greater than 1. Case 3. If c equal to 1, then the left-hand limit of f at x equal to 1 is limit x tends to 1 minus f of x equal to limit x tends to 1 minus x plus 2 equal to 1 plus 2 equal to 3. The right-hand limit of f at x equal to 1 is limit x tends to 1 plus f of x equal to limit x tends to 1 plus x minus 2 equal to 1 minus 2 equal to minus 1. Since the left and right hand limits of f at x equal to 1 do not coincide, f is not continuous at x equal to 1. Hence, x equal to 1 is the only point of discontinuity of x. The graph of the function is given in figure. Example, Show that every polynomial function is continuous. Solution. Recall that a function p is a polynomial function if it is defined by p of x equal to a0 plus a1x till a(n)xn for some natural number n, an not equal to 0 and ai belongs to R. Clearly, this function is defined for every real number. For a fixed real number c, we have limit x tends to c, p of x equal to p of c. By definition, p is continuous at c. Since c is any real number, p is continuous at every real number and hence p is a continuous function. Example, find all the points of discontinuity of greatest integer function defined by f of x equal to x, where x denoted the greatest integer less than or equal to x. Solution. First, observe that f is defined for all real number. Graph of the function is given in figure. From the graph, it looks like that f is discontinuous at every integral point. Below we explore if this is true. Case 1. Let c be a real number which is not equal to any integer. It is evident from the graph that for all real numbers close to c, the value of the function is equal to c. That is, limit x tends to c f of x equal to limit x tends to c x equal to c. Also, f of c equal to c. And hence, the function is continuous at all real number nor equal to integers. Case 2. Let c be an integer. Then we can find a sufficiently small real number or greater than 0 such that c minus r equal to c minus 1 whereas c plus r equal to c. This in terms of limits mean that limit x tends to c minus f of x equal to c minus 1 limit x tends to c plus f of x equal to c. Since these limits cannot be equal to each other for any c, the function is discontinuous at every integral point.
Algebra of continuous functions. Now, we will study some algebra of continuous functions. Since continuity of a function at a point is entirely dictated by the limit of the function at that point, it is reasonable to accept results analogous to the case of limits.
Theorem 1. Suppose f and g be two real functions continuous at a real number c, then f plus g is continuous at x is equal to c. F minus g is continuous at x is equal to c. F dot g is continuous at x is equal to c. F by g is continuous at x is equal to c, provided g of c is not equal to 0. Example, prove that every rational function is continuous. Solution. Recall that every rational function f is given by f of x is equal to p of x by q of x. Q of x is not equal to 0, where p and q are polynomial functions. The domain of f is all real numbers except points at which q is 0. Since polynomial functions are continuous, f is continuous by theorem.
Example, discuss the continuity of sine function. Solution. To see this, we use the following facts. Limit x tends to 0, sine x equal to 0. We have not proved it, but it is intuitively clear from the graph of sine x near 0. Now, observe that f of x equal to sine x is defined for every real number. Let c be a real number. Put x equal to c plus h. If x tends to c, we know that h tends to 0. Therefore, limit x tends to c f of x equal to limit x tends to c sine x equal to limit h tends to 0 sine c plus h equal to limit h tends to 0 sine c cos h plus cos c sine h equal to limit h tends to 0 sine c cos h plus limit h tends to 0 cos c sine h equal to sine c plus 0 equal to sine c equal to f of c. Thus, limit x tends to c, f of x equal to f of c, and hence f is a continuous function. Example, Prove that the function defined by f of x equal to tan x is a continuous function. Solution. The function f of x equal to tan x equal to sine x by cos x. This is defined for all real numbers such that cos x not equals to 0. That is, x not equal to 2n plus 1 pi by 2. We have just proved that both sine and cosine functions are continuous. Thus, tan x being a quotient of two continuous functions is continuous wherever it is defined.
Theorem 2. Suppose f and g are real valued functions such that f of g is defined at c. If g is continuous at c and if f is continuous at g of c, then f of g is continuous at c. The following examples illustrate this theorem. Example: show that the function defined by f of x is equal to sine x square is a continuous function. Solution: observe that the function is defined for every real number. The function f may be thought of as a composition g of h of the two functions g and h, where g of x is equal to sine x and h of x is equal to x square. Since both g and h are continuous functions, by theorem it can be deduced that f is a continuous function.
Example: show that the function f defined by f of x equal to 1 minus x plus mod x, where x is any real number, is a continuous function. Solution: define g by g of x equal to 1 minus x plus mod x and h by h of x equal to mod x for all real x. Then h of g of x equal to h of g of x equal to h of 1 minus x plus mod x equal to 1 minus x plus mod x equal to f of x. We have see that h is a continuous function. Hence, g being a sum of polynomial function and the modulus function is continuous. But then f being composite of two continuous functions is continuous.
Differentiability. We define the derivative of a real function as given below. Theorem 3. If a function f is differentiable at a point C, then it is also continuous at that point.
Proof. Since f is differentiable at C, we have limit x tends to C f of x minus f of C by x minus C equal to f dash C. But for x not equal to C, we have f of x minus f of C equal to f of x minus f of C by x minus C into x minus C. Therefore, limit x tends to C f of x minus f of C equal to limit x tends to C f of x minus f of C by x minus C into x minus C, or limit x tends to C f of x minus limit x tends to C f of C equal to limit x tends to C into f of x minus f of C by x minus C into limit x tends to C x minus C equal to f dash C into 0 equal to 0, or limit x tends to C f of x equal to f of C. Hence, f is continuous at x equal to C. Corollary 1. Every differentiable function is continuous. We remark that the converse of the above statements is not true. Indeed, we have seen that the function defined by f of x equal to mod x is a continuous function. Consider the left-hand limit. Limit h tends to 0 to minus f of 0 plus h minus f of 0 by h equal to minus h by h equal to minus 1. The right-hand limit. Limit h tends to 0 plus f of 0 plus h minus f of 0 by h equal to minus h by h equal to 1. Since the above left and right hand limits at 0 are not equal, limit h tends to 0, f of 0 plus h minus f of 0 by h does not exist and hence f is not differentiable at 0. Thus, f is not a differentiable function.
Derivatives of composite functions. To study derivative of composite functions, we start with an illustrative example. Say, we want to find the derivative of f, where f of x is equal to 2x plus 1 the whole to the power of 3. One way is to expand 2x plus 1 to the power of 3 using binomial theorem and find the derivative as a polynomial function as illustrated below.
Now, observe that f of x equal to h of g of x, where g of x equal to 2x plus 1 and h of x equal to x cube. Put t equal to g of x equal to 2x plus 1. Then f of x equal to h of t equal to t cube. Thus, df by dx equal to 6 into 2x plus 1 the whole square equal to 3 into 2x plus 1 the whole square into 2 equal to 3t cube into 2 equal to dh by dt into dt by dx. The advantage with such observation is that it simplifies the calculation in finding the derivative of, say, 2x plus 1 whole power 100. We may formalize this observation in the following theorem called the chain rule.
Theorem 4. Chain rule. Let f be a real valued function which is a composite of two functions u and v. That is, f is equal to v o u. Suppose t is equal to u of x, and if both dt by dx and dv by dt exist, we have df by dx is equal to dv by dt into dt by dx. Chain rule may be extended as follows. Suppose f is a real valued function which is a composite of three functions u, v and w. Example, differentiate sine into cos x square the whole with respect to x. Solution. The function f of x is equal to sine into cos x square the whole is a composition. F of x is equal to WOVOU into x of these three functions u, v and w, where u of x is equal to x square, v of t is equal to cos t and w of s is equal to sin s. Put t is equal to u of x is equal to x square and s is equal to v of t is equal to cos t. Observe that dw by ds is equal to cos s, ds by dt is equal to minus sin t and dt by dx is equal to 2x. Exist for all real x. Hence, by generalization of chain rule, we have df by dx is equal to dw by ds into ds by dt into dt by dx is equal to cos s into minus sin t into 2x is equal to minus 2x sin x square into cos x square the whole. Derivatives of implicit function. It is not necessary that functions are always expressed in the form y is equal to f of x. For example, consider one of the following relationships between x and y. X minus y minus pi is equal to 0. X plus sin xy minus y is equal to 0. In the first case, we can solve for y and rewrite the relationship as y is equal to x minus pi. In the second case, it does not seem that there is an easy way to solve for y. Nevertheless, there is no doubt about the dependence of y on x in either of the cases. When a relationship between x and y is expressed in a way that it is easy to solve for y and write y is equal to f of x, we say that y is given as an explicit function of x. In the later case, it is implicit that y is a function of x, and we say that the relationship of the second type above gives function implicitly. In this subsection, we learn to differentiate implicit functions. Find dy by dx if x minus y is equal to pi. Solution. One way is to solve for y and rewrite the above as y is equal to x minus pi. But then dy by dx is equal to 1. Alternatively, directly differentiating the relationship with respect to x, we have d by dx into x minus y is equal to d pi by dx. Recall that d pi by dx means to differentiate the constant function taking value pi everywhere with respect to x. Thus, d by dx into x minus d by dx into y is equal to 0, which implies that dy by dx is equal to dx by dx is equal to 1. Derivatives of inverse trigonometric functions. Inverse trigonometric functions are continuous functions. We use chain rule to find derivatives of these functions. Find the derivative of f given by f of x is equal to sine inverse x, assuming it exists. Solution. Let y is equal to sine inverse x, then x is equal to sine y. Differentiating both sides with respect to x, we get 1 is equal to cos y into dy by dx, which implies that dy by dx is equal to 1 by cos y is equal to 1 by cos into sine inverse x. Observe that this is defined only for cos y is not equal to 0. That is, sine inverse x is not equal to minus pi by 2, pi by 2. That is, x is not equal to minus 1, 1. That is, x belongs to minus 1, 1. To make this result a bit more attractive, we carry out the following manipulation. Recall that for x belongs to minus 1, 1, sine into sine inverse x is equal to x, and hence cos square y is equal to 1 minus sine y whole square is equal to 1 minus sine into sine inverse x to the whole square is equal to 1 minus x square. Also, since y belongs to minus pi by 2, pi by 2, cos y is positive and hence cos y is equal to the square root of 1 minus x square. Thus, for x belongs to minus 1, 1, dy by dx is equal to 1 by cos y is equal to 1 by the square root of 1 minus x square.
Exponential and logarithmic functions. In this section, we shall learn about a new class of related functions called exponential functions and logarithmic functions. It needs to be emphasized that many statements made in this section are motivational.
The figure gives a sketch of y is equal to f1 of x is equal to x. Y is equal to f2 of x is equal to x square. Y is equal to f3 of x is equal to x cube, and y is equal to f4 of x is equal to x power 4. Observe that the curves get steeper as the power of x increases. Steeper the curve, faster is the rate of growth. What this means is that for a fixed increment in the value of x greater than 1, the increment in value of y is equal to fn of x increases as n increases for n is equal to 1, 2, 3 and 4. It is conceivable that such a statement is true for all positive values of n, where fn of x is equal to x power n. Essentially, this means that the graph of y is equal to fn of x leans more towards the y-axis and n increases. For example, consider f10 of x is equal to x power 10 and f15 of x is equal to x power 15. If x increases from 1 to 2, f10 increases from 1 to 2 power 10 whereas f15 increases from 1 to 2 power 15. Thus, for the same increment in x, f15 grows faster than f10. For example, we can prove that 10 power x grows faster than f100 of x is equal to x power 100. For large values of x like x is equal to 10 cube, note that f100 of x is equal to 10 cube to the power raised to 100 is equal to 100 power 300, whereas f of 10 cube is equal to 10 to the power 10 cube is equal to 10 to the power 1000. Clearly, f of x is much greater than f100 of x. It is not difficult to prove that for all x greater than 10 cube, f of x greater than f100 of x. But we will not attempt to give a proof of this here. Similarly, by choosing large values of x, one can verify that f of x grows faster than fn of x for any positive integer n. The exponential function with positive base b greater than 1 is the function y is equal to f of x is equal to b to the power x. The graph of y is equal to 10 to the power x is given in the figure.
Exponential functions. Following are some of the salient features of exponential functions. Domain of the exponential function is R, the set of all real numbers. Range of the exponential function is the set of all positive real numbers. The point 0, 1 is always on the graph of the exponential function. This is a restatement of the fact that b power 0 equal to 1 for any real b greater than 1. Exponential function is ever increasing, that is, as we move from left to right, the graph rises above. For very large negative values of x, the exponential function is very close to 0. In other words, in the second quadrant, the graph approaches x-axis but never meets it.
Logarithm function. Some of the important observations about the logarithm function to any base b greater than 1 are listed below.
Is it true that x is equal to e raised to log x for all real x? Solution. First, observe that the domain if log function is set of all positive real numbers. So, the above equation is not true for non-positive real numbers. Now, let y is equal to e raised to log x. If y greater than 0, we may take logarithm which gives us log y is equal to log into e raised to log x is equal to log x into log e is equal to log x. Thus, y is equal to x. Hence, x is equal to e raised to log x is true only for positive values of x. Theorem 5. Number 1. The derivative of e power x with respect to x is e power x, that is, d by dx into e power x is equal to e power x. Number 2. The derivative of log x with respect to x is 1 by x, that is, d by dx into log x is equal to 1 by x.
Logarithmic differentiation. In this section, we will learn to differentiate certain special class of functions given in the following form. By taking logarithm to base e, the above may be rewritten as follows. The main point to be noted in this method is that f of x and u of x must always be positive, as otherwise their logarithms are not defined. This process of differentiation is known as logarithms differentiation.
Differentiate a power x with respect to x where a is a positive constant. Solution. Let y is equal to a power x. Then log y is equal to x log a. Differentiating both sides with respect to x, we have 1 by y into dy by dx is equal to log a, or dy by dx is equal to y into log a. Thus, d by dx into a power x is equal to a power x into log a. Alternatively, d by dx into a power x is equal to d by dx into e raised to x log a is equal to e raised to x log a into d by dx into x log a is equal to e raised to x log a into log a is equal to a power x into log a. Derivatives of functions in parametric forms. Sometimes the relation between two variables is neither explicit nor implicit, but some link of a third variable with each of the two variables separately establishes a relation between the first two variables. In such a situation, we say that the relation between them is expressed via a third variable. The third variable is called the parameter. More precisely, a relation expressed between two variables x and y in the form x is equal to f of t, y is equal to g of t is said to be parametric form with t as a parameter.
In order to find derivative of function in such form, we have by chain rule. dy by dt equal to dy by dx into dx by dt, or dy by dx equal to dy by dt by dx by dt, whenever dx by dt not equal to 0. Thus, dy by dx equal to g dash t by f dash t, as dy by dt equal to g dash t and dx by dt equal to f dash t, provided f dash t not equal to 0.
Find dy by dx if x to the power 2 by 3 plus y to the power 2 by 3 is equal to a to the power 2 by 3. Solution. Let x is equal to a cos cube theta, y is equal to a sin cube theta. Then x to the power 2 by 3 plus y to the power 2 by 3 is equal to a cos cube theta plus a sin cube theta to the power 2 by 3 is equal to a to the power 2 by 3 into cos square theta plus sin square theta is equal to a to the power 2 by 3. Hence, x is equal to a cos cube theta, y is equal to a sin cube theta. Is the parametric equation of x to the power 2 by 3 plus y to the power 2 by 3 is equal to a to the power 2 by 3. Now, dx by d theta is equal to minus 3a cos square theta into sin theta, and dy by d theta is equal to 3a sin square theta into cos theta. Therefore, dy by dx is equal to dy by d theta by dx by d theta is equal to 3a sin square theta into cos theta by minus 3a cos square theta into sin theta is equal to minus tan theta is equal to minus 3 to the root y by x. Second order derivative. Let y is equal to f of x. Then dy by dx is equal to f dash of x. If f dash of x is differentiable, we may differentiate 1 again with respect to x. Then the left hand side becomes d by dx into dy by dx, which is called the second order derivative of y with respect to x and is denoted by d square y by dx square. The second order derivative of f of x is denoted by f double dash of x. It is also denoted by d square y or y double dash or y 2 if y f of x. We remark that higher order derivatives may be defined similarly. If y is equal to sine inverse x, show that 1 minus x square into d square y by dx square minus x into dy by dx is equal to 0. Solution. We have y is equal to sine inverse x. Then dy by dx is equal to 1 by the square root of 1 minus x square, or the square root of 1 minus x square into dy by dx is equal to 1. So, d by dx into the root of 1 minus x square into dy by dx is equal to 0, or root 1 minus x square into d square y by dx square plus dy by dx into d by dx into root of 1 minus x square is equal to 0, or the root of 1 minus x square into d square y by dx square minus dy by dx into 2x by the root of 1 minus x square is equal to 0. Hence, 1 minus x square into d square y by dx square minus x into dy by dx is equal to 0.
Mean value theorem. In this section, we will state two fundamental results in calculus without proof. We shall also learn the geometric interpretation of these theorems.
Rolle's theorem. Let function a comma b to r be continuous on a comma b and differentiable on a comma b, such that f of a is equal to f of b, where a and b are some real numbers. Then there exists some c in a comma b such that f dash of c is equal to 0. In the figures, graphs of a few typical differentiable functions satisfying the hypothesis of Rolle's theorem are given.
Observe what happens to the slope of the tangent to the curve at various points between A and B. In each of the graph, the slopes become 0 at least at one point. This is precisely the claim of Rolle's theorem, as the slope of the tangent at any point on the graph of y equal to f of x is nothing but the derivative of f of x at the point.
Mean value theorem. Let y is equal to f a comma b to r be a continuous function on a comma b and differentiable on a comma b. Then there exists some c in a comma b such that f dash of c is equal to f of b minus f of a by b minus a.
Observe that the mean value theorem, MVT, is an extension of Rolle's theorem. Let us now understand a geometric interpretation of mean value theorem. The graph of a function y equal to f of x is given in the figure. We have already interpreted f dash c as the slope of the tangent to the curve y equal to f of x at c, f of c. From the figure, it is clear that f of b minus f of a by b minus a is the slope of the secant drawn between a, f of a and b, f of b. The mean value theorem states that there is a point C in AB such that the slope of the tangent at C, f of C is same as the slope of the secant between A, f of A and B, f of B. In other words, there is a point C in AB such that the tangent at C, f of x is parallel to the secant between A, f of A and B, f of B.
Example. Differentiate with respect to x the following function. Log 7 of log x. Solution. Let y is equal to log 7 of log x is equal to log into log x by log 7 by change of base formula. The function is defined for all real numbers x greater than 1. Therefore, dy by dx is equal to 1 by log 7 into d by dx into log x is equal to 1 by log 7 into 1 by log x into d by dx into log x is equal to 1 by x log 7 into log x. Differentiate with respect to x the following function. Sine inverse of 2 to the power x plus 1 by 1 plus 4 power x. Solution. Let f of x is equal to sine inverse of 2 to the power x plus 1 by 1 plus 4 power x. To find the domain of this function, we need to find all x such that minus 1 lesser than or equal to 2 to the power x plus 1 by 1 plus 4 power x is lesser than or equal to 1. Since the quantity in the middle is always positive, we need to find all x such that 2 to the power x plus 1 by 1 plus 4 power x is lesser than or equal to 1. That is, all x such that 2 to the power x plus 1 is lesser than or equal to 1 plus 4 power x. We may rewrite this as 2 is lesser than or equal to 1 by 2 power x plus 2 power x, which is true for all x. Hence, the function is defined at every real number. By putting 2 power x is equal to tan theta, this function may be rewritten as f of x is equal to sine inverse of 2 power x plus 1 by 1 plus 4 power x is equal to sine inverse of 2 power x into 2 by 1 plus 2x to the whole square is equal to sine inverse of 2 tan theta by 1 plus tan square theta is equal to sine inverse of sine 2 theta is equal to 2 theta, which is equal to 2 tan inverse of 2 power x. Thus, f dash of x is equal to 2 into 1 by 1 plus 2 power x the whole square into d by dx into 2 power x is equal to 2 by 1 plus 4 power x into 2 power x into log 2 is equal to 2 power x plus 1 into log 2 by 1 plus 4 power x.
Example, find f dash of x if f of x equal to sine x power sine x for all 0 lesser than x lesser than pi. Solution, the function y equal to sine x power sine x is defined for all positive real numbers. Taking logarithms, we have log y equal to log sine x power sine x equal to sine x log into sine x. Then 1 by y dy by dx equal to d by dx into sine x log of sine x equal to cos x log of sine x plus sine x into 1 by sine x into d by dx into sine x equal to cos x log of sine x plus cos x equal to 1 plus log of sine x into cos x. Then dy by dx equal to y of 1 plus log of sine x into cos x equal to 1 plus log of sine x into sine x power sine x into cos x.